Good afternoon. Just here, I want to start with chapter 8. This is going to be chapter 8, and chapter 8 is talking about mainly conservation of energy, but of course, it has to do with another type of energy that we are going to introduce, which is potential energy. Okay, then in this chapter, we are going to differentiate between conservative and non conservative forces. We will be able to find out the relation between a conservative force and a potential energy function and find the work done by a conservative force. We are going also to introduce conservation of mechanical energy, and we will solve problems. We will also, we need maybe to have the full picture, and in the sense when we have non-conservative forces, we should be working on how to calculate work done by non-conservative forces. Now also, we are going to talk a little bit about potential energy curves and equipotentials. Now, when we want to differentiate between conservative and non-conservative forces, I can say that a conservative force is a force that it has a work that can be stored in the form of energy, and it can be released and used at a later time. Okay, then this is the work of a conservative force. Okay, versus non-conservative forces, of course, their work is not going to be stored in the system. It's going to be, sometimes we're going to say, I would say lost, but I don't like this term. I like to say dissipated. The second thing is that the work done depends only on initial and final positions for conservative forces. For example, gravity. Okay, here I will say I'm gonna add a page here and talk a little bit about. Let's say I have an inclined plane, and this is really, let's say, 2 meters. And I want to bring an object from here to here. Okay, the work done by gravity is going to be the same if you bring the object from here to here directly, or if you took your object from A to B and then to C, or if you even have it like a zigzag way, but finally it will reach 2 meters away from your initial reference point. Whereas if I'm talking, of course, about non-conservative forces like friction, its work is going to depend on the actual path. Also, one thing that is really important is the work done by a conservative force. Moving an object around the closed path is zero, and this is not true for non-conservative forces. Okay, here I'm talking about, let's say I have an object that is going to be brought from here to a point here, and then I'm going to bring it back. Then here the total, I would say work done is going to be zero. And here there are these slides explain that work done by gravity on a closed path is zero. Then I am bringing my object from A to D here, and then from D to C, and from C to B, and from B to A. Remember here the work done is zero, and the work done is zero here. Why? Just ask yourself why, and if you don't know, you have to ask me. And I will say from A to D, the work done by gravity, okay, I'm sorry, like here I'm bringing from D to A. Then I will say the force is going to be in the same direction as the displacement, then the work done is going to be mgh. Whereas from B to C, I'm bringing my object from B to C, and the work done by gravity is going to be negative mgh. If you add these two, they're going to add up to 0. Also, I will say if I have here conservative and non-conservative forces, I can differentiate them from the work done by a conservative force is going to be, as I said, 0 over any enclosed path. Or we can say that the work done by conservative forces is going to be independent of the path. Now, I will say here also, for a friction, it's not a conservative force, and the reason is that its work is really depending on the actual path that we are talking about. If I have a conservative force, then I will say having a conservative force means that it will have a potential energy function, and the work done by a conservative force is going to be equal to the negative change of the potential energy function. Then this is like in general for all the conservative forces. And we know that the work done for it has a unit of joules, and U also it has units of joule. Now the work done by conservative forces, here we are displaying one of the most important conservative forces, which is gravity. And gravity, of course, it has a potential energy function that we are going to call it UG. Now that UG, it depends on M, it depends on G, acceleration due gravity, and it depends on, I would say, how high you're gonna bring your object. Then it's gonna be Y2 minus Y1. Now here, if I will talk about this textbook in the picture, if I am lifting the book to a height h, then I have two forces acting on it. One of them is gravity, and the other one, it is the force from my hand. Now the work done by the hand is going to be mgh, and it's going to be mgy2 minus y1. The work done by gravity is going to be, gravity is downward, then here cosine 180, and it's going to be negative mgh. Now, again, we can say that the work done by gravity is going to be potential energy E1 minus potential energy E2, which is negative the change in the potential energy. And we can say that the work done by gravity is going to be negative delta UG. What is really very important when we talk about gravitational potential energy, that we need to have a reference level, and that reference level is from where my y is measured. Because always I am interested in the difference in UG and not in the absolute value of UG. Okay, For today's lecture, I'm not gonna have it like long. I will make it like sections. And then here I'm gonna stop because I will talk about conservation of mechanical energy later.